is flowing, your heart is beat, so it has some response, mechanical response, and so on. So this response, so if we can use to charge up some capacitor or battery, let's say, then no need to charge the battery again, or no need to replace the battery again, right? So this is known as the self power concept. So that means we have the energy, like we are talking, or let's say we are walking and we are singing, and we are doing many daily activities every time, right? So that particular energy you no need to buy, right, or no need to produce. You have to, because if you want to sustain, then you have to walk, right, like at least 200 or 300 steps. That means you are producing a lot of mechanical energy, and it is freely available with you, right? The idea is how we can harvest such kind of energy to some useful manner. Okay, so that is the known as the new concept is the self power and electronic. And if it is like flexible, then it is known as the flexible electron. Okay, so you see this particular figure, there are a lot of electronic device, for example, tactile sensor, biosensor, and other different portable electronic gadgets, some robots, and this all eventually needs the power source. And it is possible from the different types of biomechanical energy sources, for example, blood flow, walking, finger typing, and they have wrote the energy we are producing due to the blood flow, walking, finger typing, etc. And this indicates this energy, input energy, is good enough to power up several electronic gadgets. So that means if we want to power up this such kind of device, then there is no need of any traditional power sources. So that's the idea basically of the self power. So then we have to think about what kind of materials are basically going to fulfill those particular properties. How can we make a device self power, right? So we have to think in terms of kind of material perspective. Okay, so I'm going to introduce you a very simple polymer particularly, so that you will able to understand it very smoothly. And moreover, this is basically not a expensive polymer. This is very cost effective polymer. So it is known as polyvinyl chloride. So very simple polymer. You see, this is the monomer unit. If you look, then you can see it is CH2 and CF2, right? Very simple, not like any complicated polymer, right? So as a physicist, it is always hard to follow the chemistry. So that's why I'm explaining very simple way, because so that you will not get fear, because it is very interesting polymer, engineering polymer, I would say, and very cost effective. So it is available as different form. For example, powder, sometimes pellets, sometimes kind of thick seeds or films. Okay. So as you know, PVDF is basically a semi-crystalline in nature. What does it mean? That means it has a crystalline part and it has the amorphous. So it is a mixture of crystalline and amorphous matrices. So how in physically how they look like then? If you look this particular figure, are you getting able to follow this my cursor from audience side?
Yes, we are able to see.
Okay, it's okay, fine. So you see, this is the basically amorphous matrix. Okay, and these small bricks are basically this is crystalline lamella. Okay, so all the property that we are going to talk about, like electronic property, if you touch it, it can sense. If you produce the heat, it can sense. If you apply the electric field, it can sense. So there are a lot of sensing properties are there, right? So these all the properties coming from this particular bricks types of element, which is known as crystalline lamella. Okay? So it is like if you put a like make a honey, if you place a honey and if you place a small bricks on it, or matchbox, let's say, then the matchbox are like crystalline lamella. So now then the question comes, what kind of crystallinity is there in PVDF? In short, So you see it has different crystalline polymorph. That means it has different crystalline phase. So one of the known phase is the alpha phase. So if you look, this black dot basically is the carbon, and this yellow is the fluorine, and blue is the hydrogen. So as I mentioned, this is CH2 and Cl. You see CH2 and Cl. Very simple unit basically, and this is getting repeated. Okay. However, this particular basically conformation, if you look, so hydrogen is a plus and F is the minus. This is act as a dipole. Okay. However, this particular conformation is known as trans and then gauge. So it rotates, right? So this is it's like a defect. And you see one dipole is upside, another dipole is the downside. So as a result, this particular fashion of arrangement, it possesses the dipole moment zero. Okay? So this is known as the non-polar phase. However, there is another phase. You see the bottom one, all the dipoles are in particular directions. Okay, so this is known as the beta phase, and this is a all trans conformation. So this exhibits the all better electronic properties that we are going to discuss. And this is one intermediate phase. You see this is triple TG. So like it has the three dipoles up, let's say, and one dipole down.